Okay, excellent. So our last speaker of today is Robby Deits. He will talk about JuliaRobotics.
All right, thank you. Hi, my name is Robby Deits. I'm a graduate student in the Robot Locomotion group who should definitely be writing my PhD thesis instead of being here, but I'm here, so you get to benefit. I'm going to talk about making robots walk with Julia. In retrospect, I should have titled this Towards Making Robots Walk with Julia. We're much closer than we were a year ago, but we're not all the way there yet. But I'll hopefully show you maybe why you should care anyway. So my background is that I worked on control for the Atlas robot, which is a humanoid robot, at the DARPA Robotics Challenge. So this is it's a 6-foot-tall robot, weighs about 350 pounds. That's 150 metrics. We were using it for some simulated disaster response tasks. And the primary challenge that we were working on is just getting it to walk around, balance, get from point A to point B without falling over. I started using Julia after I took Alan Edelman's class in, I think, 2016, and I've been using Julia for all of my research projects since then. In the past year, we founded the JuliaRobotics GitHub organization. Currently, it's mostly a collection of useful packages and some people who are interested in robotics in Julia. I think it has a lot of potential, though, to be a really good home for the kinds of tools that I'm going to show today that make it easier to do robotics and other high-performance tasks in Julia. Before I continue, I should mention that a lot of this work is done by other contributors from the JuliaRobotics universe. In particular, Tuan Kulin, who's another graduate student at MIT, probably wrote 75% of the code you're going to see here. Okay, so robotics is a big field. I'm not going to cover all of it. I'm not even going to cover a reasonable chunk of it today. There's the whole field of robotic hardware. Not going to go into that. The field of robotic software covers things like perception, planning, controls. There are a lot of approaches to all of those. We have explicit algorithms, things like actual control theory. We have optimization approaches. We have just throwing machine learning at it. And then we have different kinds of robotic platforms that all have different needs. Flying robots, walking robots, fixed base manipulators, cars, all require sort of different focus. So today I'm going to focus on controls using optimization for walking robots like the Atlas humanoid that I showed earlier. Okay, so what do I mean by control with optimization? So there are a lot of different approaches to robotics. There are a lot of different approaches to control even of similar humanoid robots. But at their core, all of the successful approaches right now that I'm aware of boil down to some kind of optimization performed online. So at every time step of the controller, we're going to choose, given the current state of the robot, some action. Where an action is some kind of command that we send to the joints of the robot. While respecting some kind of constraints, like the constraints imposed by physics or constraints imposed by whatever task you're trying to achieve. And we're going to try to do that to minimize some kind of cost. And so this becomes an optimization problem of minimizing that cost while respecting the constraints. We can write that slightly more mathematically, that we want to minimize over some action the robot could take, some cost of the robot's future state and actions, subject to constraints. The part that makes this hard is that the control frequencies that we use for a robot like Atlas are typically in the order of 500 to 1,000 hertz. So that means that we need to set up that optimization and solve it and retrieve the results and send those results to the robot and get new data from the robot in about 1 millisecond. So that's the entire budget we have to do everything that we're going to do to control the robot at the lowest level. That really informs the tools that we use and the way that we use them. And it makes even things like memory allocation really difficult to handle correctly. So I'm going to talk about why Julia makes this a little bit easier, mostly. So that, yeah, we'll get there. Yeah, don't worry about it. So the 1 millisecond requirement, and I mean, it's really anywhere from half to 2 milliseconds, but I think one is a good number to think about. 1 millisecond is typically meant that all of the controllers that control real humanoid robots are written in C or C++. There is one group that uses Java. It's impressive that they are able to do that. They do some really clever pre-allocation, basically. They have to fight the Java garbage collector. So I'm going to show off the tools that we've built in Julia that let us achieve the same kind of thing. So 1 kilohertz or 500 to 1 kilohertz control using optimization of a humanoid robot in Julia. And specifically, I'll talk a little bit about Rigidbody Dynamics, which is our core dynamics algorithm. I'll talk about Parametron, which is our brand new optimization front end, which is a really great 90s name that I like. I'll talk about I'll talk about MeshCAD, which is a new visualizer that we wrote since last year. Rigidbody Sim, which is our new simulation interface, which hooks into the Julia Diffie-Q universe. QP Control, which is sort of a high-level control system for robotics, and a few more useful tools. So in the last year, we put about 1,500 commits into 15 repositories. That's just the sort of public ones that I'm going to show off here. There's probably a bunch more into research code that I won't have time to get into. But we've been pretty busy since JuliaCon 2017. And so I think the state of Julia Robotics is a lot cooler than it was a year ago. So to start off with, I want to get to sort of the core of the Julia Robotics code, which is Rigidbody Dynamics, which is primarily Tuan Kulin's work. It's the most mature of all the libraries that I'm going to show, and it's the one that's sort of at the heart of a lot of what we do. So what does that mean? Well, it's in charge of things like Kinematics, which is if you know the angles of all the joints in the robot, you can tell where the hand is relative to the body, for example. That's a fundamental algorithm. To control a robot, if you want its hand to be on the table, you have to be able to figure out the mapping from the joints of the robot to where things are in space. It's also in charge of dynamics, which is just F equals ma, but with matrices. So if the robot applies this particular torque under this particular gravity in this particular configuration, how will its acceleration happen? So how will its joints change their velocity? And it's in charge of the contact handling. So how does the robot interact with the world? I'm not going to get into the details of this because we've actually already done 2 talks about rigid-body dynamics, including JuliaCon 2017. Most of those are still pretty up to date, and so we have a link to the Julia Robotics tutorials where you can see the previous talks that we've given. I do want to share that in the last year we've made some pretty cool performance improvements. I say we, I mean Tuan. Tuan has made some very cool performance improvements. So if you're not in the world of humanoid robotics, these particular calculations won't matter that much to you. But in general, this idea that, for example, dynamics of the robot is essentially F equals ma, but with matrices. So we need to compute the equivalent mass of the entire robot. That's the mass matrix. So any sort of dynamics calculation requires knowing at least the mass matrix. That's gone from 26 microseconds to 6 microseconds, which is pretty cool. Across the board, things have gotten a lot faster. Part of that is algorithmic, and also part of that is just the fact that Julia is better now, which is great. So Julia 0.7 is about just 20% faster across the board on the benchmarks. The rest of the improvement is algorithmic changes, but just being able to upgrade and have everything magically become faster is amazing. So thanks, Jeff. So yeah, this means that rigid-body dynamics, the algorithms we're showing here are competitive with things like RBDL, which is a state-of-the-art C++ library. So that's very exciting. That's a really good promise for making Julia competitive with the fastest of implementations. Okay, so I'll try to have one of these for each of the packages. So if you should try this library if you want to model the motion of some kind of rigid mechanism in space. It doesn't have to be a robot. Lots of things that have connected rigid bodies sort of look enough like robots for this to make sense. And especially if you want to do all kinds of interesting scalar computations. So if you want to pass intervals through your robot, or pass forward diff dual types through your robot, or pass symbols through your robot, all of these things just work because Julia makes it possible to compose packages to pass new types through your data without having to think about it. Okay, but on to the new stuff. So Parametron is very new. It was registered, well, the PR to register it was opened, I think, about 24 hours ago. I made these slides a few hours ago. So it's probably not even available yet, but it will be maybe by tomorrow, I hope. What does it do? Okay, so we initially used Jump to set up optimizations. Jump is great. It's the best tool for, I think, its target audience. But we're not exactly the target audience of Jump. So in particular, we care a lot, even more than your average user, about the tiniest overhead in setting up optimization problems. So in particular, if we spend 1 millisecond setting up an optimization, the controller doesn't work. That's too late. So any overhead at all is really too much. And so in the past, we got around this by mostly writing down optimizations by directly hand coding matrices in C++ and handing them to solvers, which is awful, but does work. But we can do better. This is Julia. So the other reason that we're sort of different than the target model of Jump is that we tend to solve sort of the same optimization problem over and over. So that means that the number of variables and constraints is constant. The pattern of which constraints require which variables doesn't change. The only thing that changes are the coefficient values. So as the robot moves, the masses change, the effective positions change. So we need to take advantage of that structure. So that's what Parametron does. It lets us describe the structure of the optimization problem once, and then update the values that correspond to things that change over time very, very quickly and with very low overhead. So I say it's a new front end for optimization, and I hope I don't scare you too much by saying that we're not using jump. We're not using jump, but we are still hooked into the entirety of the rest of the JuliaOpt ecosystem. The whole idea of JuliaOpt is that front ends like jump talk to a common interface, which is now called MathOpt Interface, and that talks to all of the solvers. So Parametron talks to the same interface, so that means that we get access to all of the same solvers. So we're still leveraging most of the benefits of the JuliaOpt ecosystem, just creating problems in a new way that's designed to do it with less overhead. So this is a little bit of a demo of what it might look like, solving a very, very simple model. So just like in jump, we have models and variables that are attached to those models, but we can also create parameters. So a parameter has a value, and it has a function that can update that value. And that function can refer to other parameters. And so we essentially close over any of the parameters that a new parameter requires. You can think of this as basically we're making a computation graph out of closures, which is actually, I think, very similar to what Zygote is doing. We can have constraints similar to jump. Those constraints can also refer to variables and parameters, objectives likewise. And then we can solve the model and retrieve the solution. So this is all straightforward, but the cool part is that solve function, which is updating the parameters, constructing the model for the solver, calling the solver, and retrieving the results, is super low overhead. So this is a tiny model. I mean, it's a model with one variable. But the fact that we can actually perform an optimization in 4 microseconds is insane. I've used things like CVX, which is an optimization generator. So it takes a structured problem and generates C code to solve optimizations of that form. And even that tends to take 10 to 20 microseconds for a single call. So being able to do any kind of optimization with an overhead of about a couple of function calls worth in Python is really cool. And so the key here is that now, as long as our model and our solver are good enough, the modeling tool is out of the way. And so if we can write down the right optimizations and our solver can solve them fast enough, we'll actually be able to use these in a control loop. So as I said, it works by converting parameters into closures. The closures capture the current value and whatever function is needed to update that value. And that function might also close over things like other expressions that it needs to use. Then on top of that, we have some optimizations that rewrite expressions into more efficient versions. So given something like A times B with a matrix A and a vector, A times X with a matrix A and a vector X, we'll rewrite that into creating an intermediate Y, a result, and then changing the update to always mutate that result in place. So every time the parameter A updates, we never actually allocate any new memory. We just rewrite into that same intermediate buffer. So all of these optimizations are hand-coded, and they mean that you have to sort of expose the operations you're doing to this @expression macro. However, in the magical cassette-based future, where's Jarrett? Everything will just magically work, and we won't have to think about it, right? Right? Okay. Soon. It's coming soon. So you should try this if you want to squeeze all of the performance out of your optimization framework. So in particular, if you're trying to solve small optimization problems at a rate where constructing a jump model and adding variables is actually a dominating part of the timing that you're spent, then you might actually like Parametron. And as I said, it will be registered within the next day or two, so it should be available. Okay, next cool tool is MeshCAD. So last year I showed off some visualization tools. In the past year I rewrote all of them to be better, I hope. So MeshCAD is a tool for 3D visualization. And in particular for the kind of visualization that we do in robotics. So most of what we do consists of things like loading some geometries into a scene. So for example, the links of a robot, and moving those geometries around. And usually on top of that, there's some kind of structural relationship. So in a robot, there's always sort of a tree structure that, for example, the arm is connected to the core, and the hand is connected to the arm, and so moving the arm naturally moves the hand. So this, in the graphics world, we would talk about this as a scene graph. So MeshCAD exposes the scene graph as a tree to the user, which makes it easy to describe things like robots, which makes sense as trees. It's also designed to sort of make this kind of visualization as easy as possible and to use as little code as possible. So in particular, I'm borrowing geometries from the geometry types ecosystem. That means that meshes from Mesh.io just work. Transforms come from coordinate transforms.jl. The rendering comes from 3.js, which is a JavaScript library that works in the browser. And all of the communication is handled by WebIO. So that means that actually we have an entire 3D visualizer with, I would say, only a few hundred lines of code, which is really nice. The fact that we're using a browser-based front end means that MeshCAD just works in the browser, so there's no binary dependency. It also just works in a standalone window if you use Blink, which is basically just Electron if you're familiar with that. It just works in Jupyter Notebook cells, so you can have an inline 3D visualizer inside your notebook. It should also work in Blink. I haven't actually tried it recently, but it hooks into the same machinery as, I'm sorry, it should also work in Juno, the IDE, because that hooks into the same machinery as Blink. We'll have to check that. And it doesn't require anything like VTK or GTK. And the process of installing and keeping VTK up to date has been sort of an ongoing pain for the last 5 years of my life. And now I just don't have to do that anymore. And that's great. So a little bit of demo of what you can do with MeshCAD. So to create a visualizer, we just run visualizer that initializes an empty scene. Open is just base.open. That'll open it in a new browser tab. If you use Blink, you can also open something in a Blink window, and that'll just work. And then to add an object, we just do setObject and pass it some kind of type from geometrytypes.jl. So anything that geometrytypes.jl understands should be renderable in MeshCAD. To move things in the scene, we use coordinate transformations.jl. So you call setTransform on the visualizer with, for example, a translation, and that moves the entire scene. There's also a syntax for moving just a subpart of the scene or a subpart of a subpart. And so we can create entire trees of collections of multiple robots or multiple links and move only the parts that we're concerned about at a particular time. So because we have Mesh.io and File.io, we can just load meshes. That just works. So all we have to do is load a mesh. That creates a geometry types homogeneous mesh type, which we can just set object. And I can put that inside the cat sort of folder inside the visualizer. And likewise, I can move just that part of the visualizer by moving viscat. And in this case, I'm taking advantage of the fact that composition of transformations just works. So we can compose transformations to translate and rotate things, which is a lot easier than NumPy dotting 4x4 matrices, and actually a lot more efficient. MeshCAD also supports animations natively. I don't know why I made this particular animation, but it seemed appropriate. It's a very simple animation interface. You basically create an animation, and then at frame, it passes you something that pretends to be a visualizer, which you can do things like set transformations or properties on. And then you can set transformations on later frames, and then 3JS actually just does the interpolation for you. So as long as you set these two frames, 3JS knows how to interpolate between them, and in this case, it's interpolating at 30 frames per second. Okay, so you should try this if you want to visualize some kind of tree of objects. It's probably not the most efficient for really dense point clouds. That's not something I've worked on a lot. But if you're trying to move around some relatively simple geometries, up to, say, the complexity of like a full humanoid robot, and you want to do it without complicated binary dependencies, except the browser you already have, you should check this out. Okay, the next cool tool, Rigidbody Sim. So this is the integration of robot dynamics with the entire Julia DiffEQ ecosystem. So the dynamics of the robot, when I say dynamics, I really just mean a function that maps the current state to the rate of change of that state. So f equals ma. Or in this case, x dot equals f of x. So this is the simplest possible ordinary differential equation. Now that function f could be arbitrarily complicated. It could include the entire controller of your robot, for example, but it's still just an ODE. So simulating a robot, which is something that we do all the time, just means integrating an ODE forward in time. So we can provide that function f. That's pretty easy. So we need some way to do integration of differential equations, which there's a thing for that. So we shouldn't write one. We should use the one that exists. So in particular, Rigidbody Sim provides the helper functions that bridge rigid body dynamics and the Julia differential equations ecosystem. So for example, wrapping the robot and the controller into that single function f, combining fixed rate controllers. So for example, the controller on a real robot runs at a particular rate, maybe 1 kilohertz. But the dynamics, the physics, don't. They run at no fixed rate. They run at the rate of the universe itself. And so to simulate in a meaningful way, it's necessary to combine a fixed rate controller with, for example, a variable rate simulation. Otherwise, we end up trying to solve very stiff differential equations with very large time steps, which does not work. We also have the ability to visualize robot states in real time, animate the trajectories, and even slowing down the simulation to real time. Because actually, for most of these robots, we can simulate faster than real time. And so if you want a realistic playback at real time as you're simulating, you need a way to make Julia run slower. So we have that. A demo of sort of what that looks like. So we can parse a URDF. URDF is a standard XML format for describing robots. It's something that's widely used in the robotics community. So we can load those files. We can create a controller. In this case, it's a very lazy controller. So given a vector of torques, it's just going to set all the torques to 0. So just say do nothing. We can construct a dynamics. So that's really just that function f that takes the mechanism and the controller. And then from some initial state, we create an ODE problem. That's a type from differential equations. Solve that problem with a particular integrator. I'm using RK4 here because it was what was in the notebook before, but you could use your favorite TSIT5 or anything you like. And then we can animate the result of that ODE. So what that looks like is this. So this is an animation of the solution to an ODE, rendered live. This is running in the browser because it's a browser-based tool, so why not embed it in the browser? And so we can play back the result of simulating a few seconds of motion of this particular robot. And of course, we can play it back at any particular speed that we want. And if we're interested in the particular behavior of the robot, we can investigate. And so this is the kind of thing that we've always done in robotics. We do a lot of simulating robots and animating trajectories, but it's typically involved a lot of custom code to make this possible. And so being able to use the rest of Julia geometry and Julia diffeq and combine those with our existing dynamics packages has been really powerful. Okay, so you should try Rigidbody Sim if you want to simulate these complex mechanisms without having to write your own integration schemes. And in particular, if you want a simulation pipeline that's also generic to the types. So we can do things like simulate using uncertainty propagation. So by passing measurements from measurements.jl through a simulation, we can actually get some sort of notion of our uncertainty about the position of a robot at the end of a simulation, even through the entire differential equation integration process. Okay, so now QP control, so getting sort of closer and closer to actually making robots walk. This is the optimization-based control that I was talking about at the beginning. This is the tool that's going to give us that 500 to 1,000 hertz control. It uses Rigidbody Dynamics and the new Parametron package to set up an optimal control problem. So that problem is going to choose the forces that the robot applies on the world while achieving some kind of task, like accelerating particular bodies or keeping some joints in a particular position and obeying physics. So it computes the torques to apply at each joint, and then applies them. We cascade that with a simulation, and that actually creates a controller that we can run on a full simulated robot. And this is actually enough to create a balancing controller for a humanoid robot in Julia that runs at 500 to 1,000 hertz. So the only component there that's not Julia is the actual optimization solver itself. So in this case, we're using OSQP, which is written in C. So that's just the one more thing. If somebody would just write a really good quadratic program solver in Julia, we'd just be done. And we'd have a fully Julia pipeline the whole way down. So maybe we'll do that next year. So here's the results. They're really boring because this is controls. And when things go well in controls, it's boring because the robot doesn't fall over. Like, that's it. That's simulation. But the cool part is, I mean, I'm simulating this robot, so all of the dynamics simulation, and solving the optimization for the controller at 36% faster than real time, which is pretty cool because a few years ago, the best solution we had ran at about 20% of real time. So 0.2 real time, we're now at 1.3 real time on similar hardware.
Is this guy going in and out of equilibrium and you're pushing him back in the
He's actually, what's happening is he's starting a little bit up and is sagging a little bit because there's no integration in the controller here. So there's a little, we could cause him to stand perfectly still if we passed a different set of objectives. The video's resetting every time. I'm not simulating this live. I didn't want to necessarily do that, but I did run this on my laptop last night, so it does work. Okay, so I don't have time to get into the details of all of these, but there's some more useful utilities in case you're interested. LCM is a communications package. It's similar to something like 0MQ, but it's been used in the robotics community, at least at MIT, for over a decade. So we have really nice bindings to LCM through lcmcore.jl. We also have humanoid LCM sim, which uses LCM to communicate to the physical robot. We're not all the way there yet, but that's sort of the core of how we get a controller that's running somewhere to talk to a robot that's somewhere else, visualize the results on a computer that's a third computer somewhere else, and do all of that relatively efficiently. We have some new data structures, so type-sorted collections, which is designed for heterogeneous collections of types. So if you have a bunch of things of different type, but a relatively small number of types, we can do very efficient operations on those. Tuan actually just wrote fast I/O buffers. So it turns out that Julia I/O buffers, reading or writing to them still allocates memory, which we're trying very hard to avoid. So fast I/O buffers does not allocate memory to read and write bits types, except the memory of the buffer itself. We also have enhanced GJK, so that's a collision algorithm for convex meshes. That's sort of the first step towards full collision handling, which we don't yet support. We're getting there. Okay, so I said the title of this was Making Robots Walk in Julia, and we didn't get there, sorry. There's a couple pieces. The hardware integration is a big, unknown, scary part. We're getting close. The humanoid LCM sim is the big part that lets us talk to the physical robot driver. Then there's the actual walking, which we've done. We've implemented that before, but it's a lot of work, and it's tricky to get right. And frankly, it's not our current focus of research. So it's something that I would like to happen, but being a grad student who needs to write a thesis, it's not something that I made a big priority right now. Okay, there's a little bit more from JuliaRobotics that I want to get into before I end. So we have Caesar and Rome, which are for motion estimation and simultaneous localization and mapping. Also incremental inference. This is for everybody's favorite non-Gaussian factor graphs. And I am not at all qualified to tell you what that means. But I suspect that if you're interested, if you know what it means and are interested, you'll be able to find it. We have links on the JuliaRobotics homepage. Okay, so very briefly, there were some challenges in using Julia. Being aware of garbage collection is a really big one. Because we're on a 1 millisecond deadline, pausing the world to do a garbage collection run isn't always possible. So we've tried very hard to not allocate memory ever. And so in particular, that demo of using Parametron I showed, not only was it 4 microseconds, but it was 0 allocation. That took a lot of work, and it's only possible with some of the QP solvers. So if you tried to run that with Robby as your solver, it actually would allocate some memory and would be quite a bit slower. So we're working on improving that. Fortunately, the existence of things like static arrays and just in general stack allocated bits types makes this possible. I think without those, it wouldn't really be possible to do this in Julia. That was actually a major challenge of the Java version of the controller, I'm told, because Java does not have efficient stack allocated things like static arrays. They had to do a lot more careful pre-allocation, whereas we can just return a static array and that's fine. Deployment onto the robot is still a big open question. There's no particular problem running Julia. We have big, beefy desktop machines running on these robots, but compiling the entire controller stack every time you turn on the robot just really isn't going to work. So at the very least, we need to be running something like package compiler, but that's just not something that we've investigated yet. On the other hand, the advantages of using Julia have been tremendous. So previously, we implemented this entire kind of control stack for a humanoid robot, originally mostly in MATLAB, and then later in a combination of MATLAB and C++. And that involved writing our own automatic differentiation twice, writing our own differential equations integration schemes, writing all of our own rotation handling, getting it wrong a lot before we eventually got it right, writing our own geometry primitives, our own optimization solver interfaces, getting those wrong, eventually getting them right, our own optimization front ends. I've written a couple, 4 versions of most of our code, because we had to write handwritten gradients because automatic differentiation in MATLAB is too slow. So we would have to write a version of the function in MATLAB to prototype, then a version with gradients. Then it was all too slow, so we'd port all of that to C++ with handwritten gradients, and we would maintain all 4 versions of that code for many functions. That's hard, and I don't recommend it. So in Julia, we have automatic differentiation using tools like forward diff and reverse diff, which just work and are generally fast enough to solve that problem. We have diffeq integration from Julia diffeq. We have rotations from rotations.jl, which it's not to say that there are never bugs in other packages, but now they're fixed now, and now no one else has to worry about that. We have geometries from geometry types. We have optimization interfaces from MathOpt Interface. We had the ability to use jump and then replace it with something better without having to swap out the entire rest of the solver ecosystem. I'm now using neural nets from Flux as part of my personal research on top of all of this system. So we're actually running controllers in Julia that use neural nets in Flux that were trained on the back of all of these other tools. And we only have one version of the code, and none of it is in C++. So if you want to get involved with robotics in Julia, you can check out the tools at JuliaRobotics.org. We're on Discourse, we're on Slack, way too much, just all the time. I don't get any work done, but I'm always on Discourse, so you can find me. And the most important is just run Julia on your robots. So thank you.
Questions for Robin?
Hi, really interesting talk, thank you. You mentioned there were outstanding challenges to solve with hardware integration. Is that purely what you mentioned about getting it running on the robots, or are there deeper challenges there?
No, I think that's actually the least hard. So the last time around, when we took an existing controller that worked in simulation and ported it to a physical robot, it took about, I would say, 6 person months of tuning. Because robots are not, especially the robot that we have, is nothing like its simulation. So the dynamics of the physical robot are very poorly modeled by the dynamics of the simulator. And so we, in the past, have gotten around that by a lot of grad student gradient descent, of careful tuning of parameters, which fortunately I didn't have to do. It was someone else who was much better at it. This is a completely different controller, so that tuning process, to some extent, will have to start over. It might not be as bad. We'll probably do better this time. But just the fact that the real robot is so different than the simulation means that it's very hard to make any guarantees that, oh, this worked in simulation, we can just put it right on the robot and start going. That's not a particularly language-specific feature. It's really just hardware is difficult unless your simulation is perfect.
In terms of just doing I/O, is that pretty, I'm imagining you just wrap stuff up in SQL or... Yeah,
so the I/O, we use the LCM library, and that actually sends messages out over the network as UDP. And so, yeah, the LCM core.jl wraps those with a bunch of C calls. And so we've recently been doing work on making sure that that interface is as fast as possible, so we can serialize and deserialize without allocating extra memory.
It warms my heart to see all of the composability with all of these packages in the ecosystem just working. It's just, it blows my mind every time. Like, I know we worked really hard to make it possible, but then seeing it actually work, you're just like, well, crap, that works. So I love seeing it. One of the things, about Julia is that it's dynamic and interactive, and I didn't see any of that anywhere here. And I guess my hypothetical question is, like, let's say there was a language with just as good composability and genericness and similar ecosystem, but it was all static.
Oh, okay, yeah.
Would that be better for you, or do you like the interactiveness for something?
I keep like 8 Jupyter kernels open all the time. I'm constantly editing things and running things, and mostly using Revise, so thanks for that. Yeah, I think without Revise this would be impossible, because actually it takes a long time to compile all this stuff. But yeah, we're constantly doing, editing things. We're actually making use of a lot of the metaprogramming tricks. So the way we serialize data through this communication interface, we actually have metaprogramming to introspect your Julia structs and figure out how to serialize them correctly and deserialize them. So no, I think that the dynamicness is a huge benefit. On the other hand, I think that deployment on the robot is harder because Julia isn't targeting making small, efficient binaries. That just hasn't been priority. But we do a lot more development than we do deployment in robotics, so it's worth it.
I was a little surprised by your 1 millisecond deadline, and was wondering if you'd be willing to talk a little bit more about that and how that compares to the human physiology, where like we have 3 or 4 layered systems of like 5 milliseconds, 40 milliseconds, 100 milliseconds.
Yeah, I'm definitely not qualified to like know anything about the human physiology side, but I know that humans aren't doing anything on a 1 millisecond deadline in terms of like our entire control loop. So part of it is just what do we mean by the controls? This is the thing that is choosing the torque value given the exact state measurement. So this is the sort of the lowest level that we operate at. And so, you know, it's one thing to not have the full controller that's thinking about where you're walking running at, you know, 1,000 hertz, but if you're running this at 100 hertz, so 10 milliseconds, that actually means you're holding the exact same torque value constant for 10 milliseconds. And that actually might be a problem. So it's very possible that you could restructure the way you think about this, that you could do a lower level control closer to the joints. And certainly we do things like planning where the robot's going to step. We do that at maybe 1 hertz. And planning the sort of projected trajectory of the center of mass, we might do at 10 or 100 hertz. And then it's this very lowest level of choosing the torques that we do at 1,000 hertz. But even that lowest level requires optimization.
Thank you.
How difficult was it for you to get rid of allocations? And do you have any advice for people who want to do this as well? And what tools can you envisage could make this much easier in future?
Yeah, I think Tuan is more the expert on that than I am, but so without, as I said before, without bits types, so without being able to define fixed size immutable structs that don't allocate on the heap, I think it would be impossible, or at least not practical to do. So the existence of things like static arrays and being able to build data structures that contain static arrays. So for example, we have, you know, homogeneous transforms, which is a sort of a 4x4 matrix with some annotations. Those are bits types. They don't allocate. They're free, essentially. So that makes this so much easier than it could be otherwise. The biggest challenge are tiny allocations show up everywhere. So for example, solvers use zero-based indexing because they're mostly written in C and they expect your indices to be in zero-based. Julia optimization front ends use one-based indexing. We have to transition between those. Most of the existing solver interfaces do that by taking your data and taking your Julia-based one-indexed int64s and copying those to some zero-based int32s that the C library expects. We have to get rid of all of those allocations. I spent some time trying to take an int64 vector and pack it into an int32 vector using only the front half of the existing memory, which is crazy. It's possible. It's not a great idea to try to get rid of more of the allocations in that layer. So in terms of the dynamics algorithms, it's possible, but I think it's hardest when you start meeting interfaces with the real world. Oh, but you asked about what tools, and I do have an answer. A macro that forbids allocation within its context would be great. Just turning allocation into error would make debugging much easier.
Is track allocation helpful, or is that not good enough?
Yeah, track allocation is good. I find it kind of inconvenient to use from like Jupyter.
It is.
Erroring on allocation would be great. So actually one of Parametron's features, which I didn't show, is because it's building a tree of expressions, it can actually inspect each part of that tree and ask for its individual allocations. So within that context, we can actually narrow down the allocations and verify, you know, this expression allocates because this tiny leaf in its tree allocated. Being able to do that interactively would be great, but I think being able to assert non-allocation and ensure that it's not going to show up later because an optimization went a different way would be really useful.
So would it be enough for the turn allocation into error feature to be lexically scoped, or would you also need everything in the called dynamic scope?
That's a good question. I think lexically scoped is probably fine, but cool. Okay, yeah, certainly it's better than not having it. Yeah, awesome.
Anything lexically scoped is possible.
Great, let's do it. Yeah.
Cool. Well, let's thank our speakers again.